Okay, dear students, next topic is oscillations of a loaded spring. Okay, now the vibration of horizontal spring is the first case. Here you can see here that A and B are the two ends of a spring which is attached with a load and it is resting over a frictionless table. Now suppose if we pull this block outward such that the displacement is y. So by the force law F is equal to minus ky, where k is the constant which is known as force constant, and due to this restoring force it will always tend to come back in this direction. Okay, now in this case if we let the block to be free, okay, so it will start oscillating in simple harmonic motion over a frictionless table. So now here inertia factor is, what is inertia factor in this case? It is the mass of the body. So okay, so that is equal to, we can say that, and spring factor is equal to k. This k, spring factor is equal to k. So in this case the time period t, which is having the formula 2 pi is equal to root inertia factor upon the spring factor. Okay, spring factor. So putting this value, inertia factor is m and this is k and 2 pi. So this is the formula for time period if a spring is oscillating simple harmonic motion in a horizontal direction. Now what about second case, which is the vibration of a vertical spring. Vibration of vertical spring. Now in this case the spring is hanged vertically. Okay, this is the position B and this is the fixed position A. Now suppose if we add some load to this spring. On adding the load to the spring, suppose the spring get displaced through a distance L. Okay, so in this case let we apply some load M such that the weight is acting downward. Now since the displacement is L toward the downward direction, so restoring force will act in the upward direction, and let we represent it as F1. So accordingly F1 plus mg is equal to 0 in the equilibrium condition. F1 plus mg is equal to 0, or we can write that F1 is equal to minus mg, indicating that here negative sign is indicating that restoring force is acting in a direction opposite to the direction of weight of the body. Okay, right. So from here we came to know that F1 is equal to ky also as per the force law. So here we will write KL. This is minus KL. So mg is equal to KL, or from here we can get the value of K, which is mg by L. Okay, this is the our spring factor. Now inertia factor is m here. Okay, so in this case again, suppose if we pull it more such that the next displacement is what? Okay, so spring will get more stretched. So in that case, this is the weight m, this is mg. Let the more displacement that took place is y. Initially it was L. So total displacement is L plus y. So let in this case the force F2 is the restoring force, or we can write F2 is equal to minus K L plus y. Okay. So net force acting on the system will be F is equal to F2 minus F1, which is equal to minus K L plus y and minus KL. Okay, so clearly you will see that KL factor will cancel out and we will be having F is equal to minus KY. So again we get the spring factor exactly same K, which is the same as the force law. Okay, so now putting time period T is equal to 2 pi root of m upon, this is K. M is inertia factor, K is spring factor. So putting this value of K here, 2 pi root of m, K is m, G, L taken up. So we'll be having 2 pi root of L upon G. So this is the expression for time period for a spring which is oscillating in a vertical direction. Okay.